name's Kalina and this is Emily Bennett.
And we are here to talk to you about thermodynamics.
First, let's start with the foundation of thermodynamics, the 3 laws of thermodynamics.
The first law of thermodynamics is that energy can be neither created nor destroyed.
The second law of thermodynamics is that in any spontaneous process, there is always an increase in the entropy of the universe.
The third law of thermodynamics is that the entropy of a perfect crystal at 0 degrees Kelvin is 0.
Now for 2 of these laws, we mentioned something called entropy. Entropy is a measure of the number of specific ways in which a thermodynamic system may be arranged, commonly understood as the measure of disorder.
Basically what that means is entropy is chaos. Here are a few examples.
In this example, we are showing how when gas is in a confined space, such as a balloon, there is less entropy. When it is released, the particles spread out, therefore there is an increase in entropy.
Ice is the solid form of water. It has very low entropy because the particles are organized. When the ice melts, the entropy increases because the particles spread out randomly. We also boiled the liquid water to increase the entropy even more. When the liquid turned into steam, the particles spread out even further, creating more chaos.
As you just saw, we turned liquid water into steam and we turned ice into liquid water. This was an example of entropy because the substances became more disorganized. This is what was really happening. You had ice in a close packed shape that was really well organized, and when it turned into liquid water, it spread out more. And in the liquid water, when we boiled it and it turned into steam, the particles spread out even more and became even more disorganized.
In our last example, we dissolved sugar in water. We placed sugar in room temperature water and in hot water. As the water dissolved, the entropy of the solution increases. The substances are no longer water and sugar, but instead 2 randomly mixed substances swirling around in an aqueous solution.
Spontaneity is whether a reaction will go naturally on its own or whether it will require an energy input.
For our first example, we put Mentos in Coke and Diet Coke. This shows how a reaction proceeds without any intervention. We did not add heat or stir the solution. The reaction simply happened.
Another example of a spontaneous reaction is the rusting of metal. Here you can see multiple metal objects with no rust, but as they come in contact with water and are oxidized over time, they rust.
This is the burning of paper. As heat is added to the paper, it combusts and forms carbon. However, the reverse reaction is non-spontaneous because paper does not put itself back together from basic carbon.
For our last example, we are showing again the melting of ice. Ice spontaneously melts when placed in hot water, but the reverse does not occur. Ice will not spontaneously reform when it is in hot water.
As you can see, we use the melting of ice in hot water for both spontaneity and entropy.
This is because the two are related through the concept of free energy.
Free energy is a thermodynamic quantity equivalent to the capacity of a system to do work.
Gibbs' free energy equation shows the relationship between free energy, entropy, temperature, and enthalpy. Enthalpy is a thermodynamic quantity equivalent to the total heat content of a system.
If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is non-spontaneous.
Now we will show you a problem that we worked out to find if a reaction is spontaneous.
We are given a few things at the beginning of the equation. We are given that the temperature in Kelvin is 298 degrees. The change in entropy is negative 0.19875 kilojoules per Kelvin, and the change in enthalpy is negative 92.22.
Now we plug these values into the equation. The final amount of change in free energy is negative 32.96, which means that the reaction is spontaneous.
Now we will find the temperature at which something spontaneously happens.
Sodium carbonate can be made by heating sodium bicarbonate. Given that delta H is equal to 128.9 kilojoules per mole and delta G is equal to 33.1 kilojoules per mole at 25 degrees Celsius, find the temperature at which the reaction becomes spontaneous. The complete equation can be seen on the paper.
First of all, we know that delta G is equal to delta H minus T times delta S. So first we must find delta S. We do this by making 33.1 kilojoules per mole equal to 128.9 kilojoules per mole minus 298 Kelvin times delta S. Then you get delta S by itself, which would give you delta S is equal to 33.1 kilojoules divided by moles minus 128.9 kilojoules divided by moles divided by negative 298 Kelvin. After doing the calculations, you get delta S to be 0.321 kilojoules divided by moles times Kelvin.
Now we go back again to the initial equation. Delta G is equal to delta H minus temperature times delta S. The reaction will now be equal to 0 because the reaction becomes spontaneous when delta G is 0 or below 0.
Finally, you make the equation equal to T and solve it. And the final answer will be T is equal to 401 Kelvin.
Thank you for watching our presentation.
And we hope you learned something about thermodynamics.